A-PEGASUS, Airborne Portable Electric Generation and Storage Universal System. The full system comprises a tethered aerostat that houses a horizontal axis wind turbine, a set of control systems to regulate the internal pressure and altitude of the tethered airship, and a hydrogen generation, recovery, and storage system. For the sake of simplicity, the first The tethered aerostat is filled with hydrogen gas so that it is buoyant in the atmosphere, and also features the geometry of a high-efficiency concentrator diffuser wind turbine augmenter, namely a volume of revolution with an airfoil cross-section. The design includes feedback control systems to regulate the pressure of the hydrogen gas and the rotational speed of the wind turbine rotor. The technology also features systems that retract and deflate the aerostat to protect it from severe weather, and that prevent damage to the assembly from static discharge and lightning strikes. The system can carry additional payloads, enabling it to perform other missions, including meteorological observation, reconnaissance, aerial surveillance, and radio telecommunications. The preliminary research for the current project included the optimization of the geometry of the wind augmenter through a series of computational, analytical, and experimental methods. The computational fluid dynamics simulations were performed for a range of augmenter geometries in order to determine the optimum set of concentrator and diffuser angles. The analytical portion comprised the derivation of a new, more elegant set of mathematical relations to predict the efficiency of the augmented turbine in terms of only free stream wind velocity and 4 pressure coefficients. During the experimental portion of the research, a series of 3D printed scaled models, and finally a 60-watt model, were tested in a wind tunnel. The results were used to verify the computational simulations. The development of a fully operational prototype was completed in 7 steps. The design and performance specifications were developed for 3 different ranges of possible power output for the scaled flight test model: 5 watt, 50 watt, and 0.4 kilowatts. The largest model was selected as the most feasible concept demonstrator and was fully integrated into the future design stages. 6 airship designs were evaluated and quotes were requested from 5 different manufacturers in the United States and Canada to determine the most cost-effective design. The selected configuration was a single wind augmenter lifted by 2 conventional tethered aerostats with a length of 7 meters and total lift capacity of 20 kilograms in standard atmospheric conditions. 12 different commercially available wind turbines were evaluated on the basis of their power output, weight, voltage, and cost. A Primus Air 30 turbine was selected and used as the basis for the subsequent design and stress analysis of the flight test model. Analytical and finite element stress analyses were performed on the turbine, augmenter frame, augmenter skin, and airship. The final materials for construction were selected, purchased, and shipped to the researcher's house for assembly, including 2 airships, 40 meters of aluminum tubing, the Air 30 turbine, a deep-cycle lead-acid battery bank, heat-shrinking polyester film, and 65 meters of copper-plated aluminum transmission wire. The steps of assembly are documented in the media gallery at the following YouTube website. The development process. A flight test plan was developed and site chosen for the static and dynamic tests. The necessary instrumentation for the turbine testing program was selected and purchased, including a custom-built watt transducer, data logger, and custom digital battery regulation system. The airborne generator did not exhibit any negative flight characteristics, such as excessive oscillations, porpoising, flutter, etc. The augmenter generated significant amounts of lift and sustained winds, as predicted by the CFD simulations. The concentrator diffuser geometry of the wind augmenter assisted the aerostat's tail fins in yawing into the oncoming wind. The custom-built instrumentation was selected and programmed by the researcher for a collection of the power performance data. The data was analyzed with MATLAB to create the cost analysis of the technology. As predicted by the CFD models, the augmentation of the Air 30 turbine increased its performance nearly to that of the theoretical Betz limit of 59.3%. When the power output of the turbine exceeds 400 watts, the automatic electromagnetic brake activates, slowing the turbine, as shown in the following graph. Follow-up research and development is recommended to advance this technology in the following areas. Replace the current aerostats with models designed to be compatible with hydrogen and rated for extreme winds up to 20 meters per second. Develop and implement the hydrogen generation, storage, and recovery system for use in the aerostats. Develop a set of ground controls that would enable fully autonomous operation of the system. Substitute a grid-connected induction generator in place of the current permanent magnet alternator. Implement Grade A aircraft Dacron fabric for the wind augmenter, used in an earlier 60-watt wind tunnel model, rather than the polyester film which had a strong tensile strength but poor puncture resistance.
And oh, my soul so weary, when troubles come and my heart burdened be, then I am still and wait here in the silence until you come and sit a while with me. Raise me up so I can stand on my